Hello, this is Jack Jackson. In this video, we're going to be looking at the vector form of a 2D parametric curve. So we're going to be using vectors to represent motion of a particle along some path in a plane in 2 dimensions. So we can give the position of a point or a particle at time t by a vector. This is essentially the same thing as giving parametric equations for that curve. Here's the 2D version of that. The r vector as a function of t is some x of t, y of t. Now the x of t is the parametric equation for x in terms of t, and y of t is the parametric equation for y in terms of t. So if we place this vector with the tail at the origin of some coordinate system, then the tip of that vector will be at the point, at the particle, where the particle is. Okay, so as t progresses through some interval, we see how these vectors change, indicating where the point or particle is at a particular time. So we can think of t as being time, and this will show the motion of that particle. So for example, let's see if we can do this one. Let the r vector be t squared, comma, t cubed minus 3t, and we're going to let t run from -2 to 2. So we want to graph the curve and illustrate the position vector for a particular point, let's say for t equals 1. See if you can do this on your own right now. Well, hopefully you were able to do that. It's basically just the same thing as graphing this with parametric equations. X of t equals t squared, y of t equals t cubed minus 3t. Let t go from -2 to 2. You'll get the curve graphed out, and if we plug in t equals 1 in here, we'll get the coordinates of the xy coordinates of the point on there, and the vector is just going from the origin to that point. So here's what we end up getting. It actually starts down here, traces around this way, and ends up back here at x equals, or t equals 2. Starts down here at t equals -2, t equals 0's here, but t equals 1, it's this point right here. So this vector is r of 1. It's the vector 1, -2. Go to the right 1 and down 2 gives us this point here, which is a point on this particular graph. Okay, so I'm going to look at this GeoGebra sketch and see how this looks. I basically followed the sketch created by George Sturr and just slightly modified that from what he basically changed a few cosmetic things from what he had. So let's take a look at this. And here is the sketch. Here is the graph here. And you can see the point moving around as it goes around through time. Here's the time changing. And then here is the position vector given here. And I can animate this. And so we can see as the time goes forward, we can see where the position is. You notice it may be going slower in some places, and it may be moving more rapidly in other places. So we have different velocities. So now it's going kind of slowly here. Now it's going to pick up some speed. It's going to go around a curve here and then head back out as it's going out to the upper right. And so all of those vectors there are just position vectors. Of course, a vector can be placed in any position you want it in terms of the initial point, but when we want to interpret it in terms of a position vector, it definitely makes more sense to think of it as the initial point as being at the origin. So this is a position relative to some coordinate system that we have there. Now, one of the things we might be interested in is how fast is this particular particle moving at any particular time. Okay, and we noticed some places it was moving a little faster than others, and we had what direction is it going as well. Well, that basically leads us to the idea of a velocity. And velocity is just the derivative of the position vector. Let me go ahead and show it to you. And it's kind of too long to see here. Let me see if I can zoom in a little bit so you can see the entire thing. There you go. And then let's animate that starting at t equals -2 and see what happens. Notice that the velocity vector is always tangent to the curve. Okay? And it points in the direction of the motion. It's sort of an instantaneous direction of travel, and instantaneous, and that's the direction of it, and the length of it is the speed of the particle. And so as that green vector gets moving longer, you can see that the particle is speeding up. Okay, so that's the velocity vector. Okay, so let's continue on. So that turns out to be a derivative. So the first derivative of position vector is going to be the velocity vector. And of course, you can see how the definition of this thing would work. The velocity vector is the derivative of the position vector. R and V are used for these things. R for position, V for velocity most of the time. So of course, a definition of the derivative would be R of t plus delta t minus R of, that should just say t, and then delta divided by delta t. Okay, there it is. And then take a limit as delta t approaches 0. Of course, R of t plus delta t means x of t plus delta t, comma y plus evaluated at t plus delta t, minus R of t is just x of t, comma y of t, that vector. Now, because of the way we know how vectors work, these are subtracted component-wise. Dividing by a scalar just distributes into both parts, and then the limit of a vector function we know is just the limit of each part. And so this you see is just x prime of t, and that's y prime of t. So how do you find a derivative of a vector function? Well, you just take the derivative of each component. I've worked it out here for 2 dimensions, but it would work the same whether you had 3 or 4 or 5 or 6 dimensions. You just take the derivative of each piece, and that's the r prime vector. And we're going to interpret that, and if we interpret the r vector as a position, then the r prime is interpreted as v, the velocity. So in our particular example, we had r is given by the function t squared, comma t cubed minus 3t for t going from -2 to 2. See if you can figure out the velocity vector as a function of t, and then also the specific velocity vector when t equals 1. You should be able to do this on your own right now. Press pause and try it yourself. Okay, I hope you tried it yourself. Let's see what happens as we look at it. So here is the r vector in blue, which is right here for t equals 1. There's the curve. And the velocity given in green is, as a function of t, is just going to be the derivative of each part. It's r prime of t. So you take the derivative of the t squared is 2t. The derivative of the t cubed minus 3t is 3t squared minus 3, or 3 times t squared minus 1. Okay. Or even 3 times t plus 1 times t minus 1 if you'd rather. But in any event, there it is. There's one version of it. Plug in 1 in this formula where the t's are, and we see that this is the vector 2, 0. So that this point right here, the velocity vector is 2 units long, and it's pointing directly to the right. 2 to the right, 0 up and down. The speed of the object is the magnitude of that velocity vector, its length, which is the norm of that. So you just square each component, add them up, and square root. So as a function of t, here's the scalar function that is the speed. So it's 2t squared plus then the 3t squared minus 3 squared. Okay, let's see. 3t squared, we square the first term, that's 9t to the fourth. We square the last term, that's plus 9. For the middle term, we multiply and double it. That's -9, double is negative 18t squared plus this 4t squared is negative 14t squared for the middle term. Of course, that's all under the square root. So that's a function of s. If you were to plug in 1 into this, you get 9 minus 14 plus 9 is 4. Square root of that is 2. And of course, it's pretty easy to see that the length of that is 2. Or if you take this one here, 2 squared plus 0 squared is 4. Square root of that is 2. So the speed there is 2 units. What would be appropriate units? I guess the x and y coordinates could be given in some length units like meters. T could be given in some time unit, say seconds, and then R would be given in meters, and then V would be given in meters per second. So this gives you that vector. This is 2 meters per second is the speed, instantaneous speed, and the direction is exactly to the right at that instant. So notice that the velocity vector is always tangent to the curve and is pointed in the instantaneous direction of the motion. The magnitude of the velocity is the speed of the particle and the length of the velocity vector. Next, we might look at the second derivative of a position vector, or the derivative of the velocity, and that is known as the acceleration vector. So notice in general that position, velocity, and acceleration are actually vector functions. They have a magnitude and direction to them. And likewise, you just do component-wise derivatives once more. So if we were to apply this to our problem example that we have, remember we had r of t is t squared, comma, t cubed minus 3t. We did derivatives to find the velocity vector, r prime of t was 2t, comma, 3t squared minus 3. Take another derivative, and we get 2, comma, 6t for the acceleration vector, and that's as a function of t. It looks like this particular one always has a constant component to the right of 2, but the up and down component varies depending on what t is. Okay, in our particular point, when t equals 1, this is 2, 6 for the acceleration vector, which you can see right here. So how can we interpret a couple of these things? Well, once again, note that the velocity vector is always tangent to the curve, and it's pointed in the instantaneous direction of the motion. The magnitude of the velocity is the speed of the particle and the length of the velocity vector. We can resolve the acceleration vector into two components, one in the direction of motion, that's called the tangential component because it's going to be tangent to the curve, and to find that, it's just the projection of the acceleration vector onto the velocity vector. And then there's the component that's perpendicular to that. That's called the normal component. So if the tangential component of the acceleration, it's going to be, well, it has two possibilities. It could be in the same direction as the velocity vector, or it could be the opposite direction. It's going to be on that same line, but it could be either the same or opposite direction. If it's in the same direction of the velocity vector, then basically the magnitude of the acceleration will be measuring the increase in speed, the rate of increase in the speed. If the normal component of the acceleration is in the opposite direction of the velocity vector, then its magnitude will be measuring the decrease in speed. So you'll be decelerating. The normal component of the acceleration is actually measuring the change in direction of the particle. So if the normal direction of the normal component of the acceleration is 0, then the particle will stay in motion in a straight line, the same direction as indicated by the velocity vector. But if the normal component of the acceleration is not 0, then the path of the object will curve toward the direction of the normal component. So if it's sort of more to the left of the path when you're facing the direction of the velocity vector, then you're going to turn that way. You'll turn to the left. Before we look at the next example, let me point out that the velocity vector is is horizontal, and that's not always the case. So the components here of the acceleration, in the next case, well, I'll go ahead and show it to you. This next one here are actually horizontal and vertical, but that's not usually the case. I'll show you some examples in a minute where they're not. So this black one here is in the same direction as the velocity vector. In this case, it's actually the same thing as velocity vector. And the orange one is normal or perpendicular to that. If you add those two vectors together, you get this acceleration vector. So let's find the acceleration vector. It's the projection of the acceleration vector onto the velocity vector will be this tangential component. So let's find the tangential component. It's the projection of A onto V. And if you remember from earlier work, we saw that that was A dot V divided by the norm of V squared and then times the vector V. So A was 2 comma 6t as a function of t. V as a function of t is 2t comma 3t squared minus 3. We're going to dot product those two. The norm of V is the square root of 9t to the fourth minus 14t squared plus 9. We're going to square that square root, which will cancel the square root there. And the dot product here in the top is 4t. So it's 2t times 2 is 4t. 6t times this is 18t cubed minus 18t. And I can combine like terms here. That's 18t cubed minus 14t. And I simplified, or I don't know if it's simplified or not, I factored it anyway. Factored out a 2t here and made this 9t squared minus 7 times 2t. Now all of that still is a scalar, at least a scalar function, and it's going to be multiplied by this vector function over here, which is the vector v as a function of t, which means it's just distributed times each one. So if we do that, then the x component of this tangential component is given by 4t squared times 9 parentheses 9t squared minus 7, close parentheses, divide by 9t to the fourth minus 14t squared plus 9, and then comma, and I, well, at least partially factored this, 6t times t squared minus 1 times 9t squared minus 7, and that's over 9t to the fourth minus 14t squared plus 9. If we plug in specifically t equals 1 in this formula, you're going to see that t squared minus 1 is 0, so this second component is 0, which is what we expect. Since the velocity vector second component is 0, it's pointing straight to the right. It's going to be some scalar times this 2, 0, right, which is this vector right here with a 1 plugged in. That's 2, 0. And in fact, it is just 2 zeros as well. When you plug in 1 here, let's see what happens. 1 here and 1 here is 9 plus 9 is 18 minus 14 is 4 for the denominator. 1 squared is 1 times 9 is 9 minus 7 is 2. That's a 1. That's a 2, 4. 4 times 2 on the top, a 4 on the bottom. The 4's cancel. You're left with just 2. So the acceleration is 2, 0. The tangential component of the acceleration is 2, 0. And it turns out the normal component is then 0, 6. Because this is just 2, 6. We'll talk a little bit later on how to find that normal component a little bit better. Of course, there's a right angle there. So for our example, summarizing, here's our picture. The point is right here. It's at the coordinates 1, negative 2, and that you can see by the r vector. This is corresponding to t equals 1. At that particular point, the velocity is 2, 0. So we're going this way with the speed of 2 distance units per time units, whatever that would be. Notice that's tangent to the curve. The speed is the magnitude of that, which is 2. The acceleration is pointing this way. So notice that it has a component going in the same direction. That's going to have a tendency to make this thing speed up. So at this point, this particle is picking up the pace. It's picking up speed. Okay, and this orange component, since it's pointing if you're to the left, if you're facing the direction of the velocity vector, the orange vector is the normal component, which is 0, 6. That's pointing to your left. That means you're turning to the left. So if you're facing sort of forward and moving this direction, you're going to be doing a left turn here. Okay? And so this gives you an idea. Now think about if you were driving a car along this path, what would we see? What can control this tangential component and normal component? Well, the tangential component is the component of the acceleration that's going in the direction you're going or backwards from that, which is controlled by your gas pedal and your brake pedal, right? As you press down the gas, the tangential component of acceleration is getting bigger, so you're speeding up. And if you put on the brakes or ease off the gas, then the tangential component is going down. The normal component is controlled largely by the steering wheel. In this case, we've got our wheel turned to the left a little bit. So here it is, and here's the acceleration vector. And let's look back here, and I'm going to animate this starting at -2 to +2. And this is going to trace through time consistently so that the increments of t are increments of some time. And you can see what's happening with this. So again, notice that green vector is always tangent to the curve. That's your velocity. Okay, and then the acceleration vector is basically, in this case, pointing to the left. So we're going to be making left turns kind of throughout here. Okay, but now more of that vector is pointing against the direction of the velocity, and so we're slowing down. Now we're speeding back up again because they're going more in the same direction. So now if we wanted to see along with that, we could see the components. Let's see, here we go. So here are the components of the here we go. How about right here? You can see this black vector is a component of the acceleration in the direction of the green velocity vector. So that's the tangential component. It's tangent to the curve. And perpendicular, if we move this over, it would be perpendicular to the curve, is this normal component, the orange one. Okay, so you can kind of see that. And again, I'll let this run for a minute and go through what we see here. And you see here that the vector is slowing down because the black and green vectors are opposite. Now they're going to be going the same direction, so it's going to be speeding up. Every time, if you're pointing in the direction of the green, the orange vector is at least somewhat pointing to the left. So this is some kind of curving going to the left. So we got our steering wheel, if you will, turn to the left here. Not always by the same amount, though. Okay. So in this next slide, you'll see basically certain shots from what we just did in animated form. Here you can see them sequentially side by side with different time values. T equals -2, T equals -1.5, -1, 0, -0.5, 0, 0.5, 1, 1.5, and 2. So in increments of t going up by half all the way from -2 to 2, I've got those vectors graphed. So the blue vector is the one starting at the origin. That is the position vector. The green one that's pointed in the direction of the motion at all times and tangent to the curve, that's the velocity vector. The red one is the acceleration vector. Okay, and then it has two components. One is either going the same or opposite direction from the vector, that is the velocity. That's going to be the normal component, the tangential component, excuse me, tangential component, because it's tangent to the curve. And the normal component is the orange vector. So by having those sequentially, you can kind of compare them a little bit to each other across, and you can also have some notes that don't depend on the dynamic thing. The dynamic thing is probably the best. Now, what we can also do sometimes is we're mainly interested in not necessarily only just the magnitude, but just the basic direction of that velocity vector. And so you want to basically take that velocity vector, get rid of the speed by dividing by the speed, dividing by that norm. That gives us a unit vector that's going in the same direction as the motion, right? The same direction as the velocity vector. But it's a unit vector. Of course, it's tangent to the curve. So that's going to be what we call a unit tangent vector, and that'll be given by this capital T vector. Then we have a principal normal vector to that. That's a vector that's perpendicular to that. And I'll explain later on when we do this in 3D why this formula here always gives you something perpendicular. But it turns out if you take the derivative of that T vector and then divide by the norm of the derivative, then that gives us a normal vector that's unit vector. Okay, so it's going to always be perpendicular to the velocity curve, and that's given by the little brown vector, and the purple one's the unit tangent vector. So let's look at that dynamically in our GeoGebra thing here. So let me kind of put everything back here, and if we look at, let's take away the acceleration stuff. And so we just have the velocity vector here, and notice that the green velocity vector is going to be changing in length, but if you always scale it down to a length of 1, you get this unit tangent vector t, which is right here, and then this is just a perpendicular to that. Okay, and so again, I'll animate that, and so you can see that as it goes around here. I'll turn off the velocity vector. So now we're just seeing those two unit vectors go around. I'll even take away the position vector. And so once again, we can see this as we move. I'll go around a little faster, but you can see as we move around, the purple one is giving you the direction that we're going, and the brown one's just perpendicular to that. It's a normal vector. Okay. All right. Finally, one final thing that I want to go over very quickly is that since derivatives of vector functions are just computed component by component, antiderivatives and integrals are going to be computed the same way. So notice that the arbitrary constant of integration, it's usually like plus c back in Cal 1, is going to be plus some constant vector. The plus c is a constant scalar, constant real number, arbitrary, and the Cal 1 functions that we did when we integrated. So we got a family of antiderivatives, and the family of antiderivatives here, the plus c is going to be replaced by plus some c vector, some constant vector, but which is arbitrary. So, for example, r of t is given by x of t comma y of t as that vector. Then the integral of r of t is just the integral or the antiderivative of x of t dt for the first component, and the antiderivative of y of t dt for the second component. Very straightforward way of setting it up, and of course that's going to lead to the same kind of thing for definite integrals, allowing us to use the fundamental theorem of calculus on each piece. And so we get the r of t dt. You want to do a definite integral from some time 1 to time 2, t1 to t2. And so that's going to be the integral from t1 to t2 of x of t, y of t dt. And this, of course, that's one vector, which each component is an integral or a definite integral itself. So that's the integral from t1 to t2 of x of t dt, comma, the integral from t1 to t2 of y of t dt. And once again, in the first part, you're going to get a plus c1 here, plus c2 here, and then your plus, which you can pull out as a plus c1 comma c2. So that's a vector constant there. All right, so that'll give you a basic introduction to that. This is pretty important stuff, but it's pretty straightforward. It's just basically work with the components and do the kinds of things that we've been doing before.